Okay, so this is the solution to the growth problems. Let's take a look at number one. You have the number of bacteria is growing at a rate, so they actually give us the growth rate. R of t is 3,000 e to the 2t over 5, right? Okay, so what we're being told is that at time 0, there was 7,500 bacteria present in the experiment. All right, so this works just like an accumulation problem. We know that the integral from 0 to 5 of 3,000 e to the 2t over 5 dt should equal p of 5 minus p of 0. P of 0 is 7,500, so p of 5 is going to be 7,500. That should be like a p. That's the population at time 0, right? Should be 7,500 plus the integral from 0 to 5 of 3,000 e to the 2t over 5 dt. All right, so this is 7,500 plus 3,000 times 5 halves e to the 2t over 5 from 0 to 5, right? So this is what's the integral here. This is 7,500. I keep saying 75,000. That's 7,500. This is also going to be 7,500. And then we're going to be like e to the second minus e to the 0. All right, so that's 7,500 plus 7,500 e squared. E to the first is 1, so that's going to be minus 7,500. And lo and behold, those fall out, giving me 7,500 e squared, which is C. So there you go. Let's look at problem number 2. Bacteria in a certain culture increased at a rate proportional to the number present. So dp dt is proportional to the current population. So if you solve this, you're going to get that the population is equal to the population's initial value times e to the kt. We have an initial value in this problem. We're told that the bacteria doubles in 3 hours. So we're going to have 2 times the initial population when t is equal to 3. So those cancel, giving me that 2 is equal to e to the 3k. The natural log of 2 is equal to 3k. K is equal to the natural log of 2 over 3. So now what we want to know is what time does the population triple? So 3 times the initial population should be the initial population times e. K is the natural log of 2 over 3 t. Again, that cancels, so 3 is e to the natural log of 2 over 3t. The natural log of 3 is equal to the natural log of 2 over 3t. And we multiply this by the reciprocal, so 3 times the natural log of 3 over the natural log of 2 is equal to t, right? So that solution, I believe, is letter A. All right, so there we go. Let's look at number 3. Okay, so we have a puppy weighing 2 pounds at birth and 3.5 pounds 2 months later. So if the weight of the puppy during its first 6 months is increasing at a rate proportional to its weight, so weight is equal to or change in weight with respect to time is equal to k times the weight. That's that statement. How much will the puppy weigh when it's 3 months old? So this becomes current weight is weight, initial weight times e to the kt. We know that the initial weight we know is 2 pounds. We know it's 3.5 pounds 2 months in. So 1.75, I think that is, right? Or no, 1.75 is equal to e to the 2k. The natural log of 1.75 is equal to 2k. So k is equal to the natural log of 1.75 over 2. All right, so we want to know the weight at 3 months, right? So that's going to be 2 times e to the natural log of 1.75 over 2 times 3. If you throw that into a calculator, you're going to get approximately 4.63, which is B. All right, so that's 3. All right, so let's look at number 4. During a certain epidemic, the number of people, yes, the irony, the number of people that are infected at any time increases at a rate proportional to the number of people infected at that time. So the change in population infected is equal to some constant times the population. If 1,000 people were infected when the epidemic is first discovered, and 1,200 were infected 7 days later, how many will be infected 12 days after the epidemic is first discovered? So again, we know that this means that P is equal to P initial e to the kt, right? So P is the initial value is 1,000, right? E to the kt. We have an initial point for 7 days in, so 1,200 is 1,000 e to the 7k. So we divide both sides by 1,000. We get 1.2 is e to the 7k. The natural log of 1.2 is equal to 7k. K is equal to the natural log of 1.2 over 7. Okay. So that being said, P at times 12 will be 1,000. E to the natural log of 1.2 over 7 times 12. You put that in a calculator and you're going to get approximately 1367, which is C. All right. So that's it for problem number 4. Okay, let's look at number 5. 5 gives me the growth equation. So it tells me that dy dt is equal to some constant times y. That implies that y is equal to the initial value of y e to the kt. We know that the population doubles every 10 years. So 2 times y null should equal y null e to the 10k. The y's cancel, so 2 is equal to e to the 10k. We take the natural log of both sides, and then we divide by 10, which tells me that k is equal to the natural log of 2 over 10. And if you throw that in a calculator, you're going to get approximately 0.0693, which is answer A. All right, number 6 is a bit of a tricky problem. They give me this model. dm is equal to dt, which is equal to 0.6 times m. So the 0.6 here is the k. M is actually the total size of the population. in this model. So the 200 here is actually the carrying capacity. Okay, so M is the size of the population currently. 200 is the carrying capacity. So this is a bit of a trick question because it says what is the limit as t approaches infinity of the population as time goes to infinity? Well, that is the carrying capacity. So you can go through and use like that the population starts at 50 and work all the math of this problem, but the fact is that the population is going to approach its carrying capacity in this model, which is 200. So the answer here must be B. It's really that simple. You just got to know what's going on in the equations. Okay, so let's look at problem number 7. 7 says that the rumor is spreading at a rate that's proportional both to the number of people who've heard the rumor and the number of people who are who have not heard the rumor, right? So this is the rate at which the rumor is spreading, dp dt. That it's proportional is k. The number of people who've heard the rumor is p. The total population is n, so the people who have not heard the rumor is n minus p. And that's pretty much the straightforward problem there. So the answer there is B. All right, problem number 8 takes a little bit of futzing around and some looking at the diagram that's there. We know that we have an example of logistic growth here because of the shape of the curve. So dp dt has to be some constant times the current population times 1 minus the population over the carrying capacity. Okay, so playing around with this a little bit, this gives me kp minus kp squared over m. Looking at the diagram, we know that the carrying capacity has to be 200. So we know that k over 200 is going to be less than k. So that means that my answer choices here are either A or B. It's the only way it's going to work. If we look at this, we are also told there that k over 200 is going to be 1/1000th, right? So if I try to solve this equation, I get k is equal to 200 over 1,000, which is 2 over 10, which is 0.2. And the one that fits that then would be that I get 0.2 times p minus 0.001 times p squared. So the correct answer there will be A. All right, looking at number 9, it asks which one of these are linear growth. Linear growth has a constant rate of change, so the rate of change of the population has to be some constant. The only answer where I have a constant rate of change is A. Sometimes it's a softball, sometimes it's that easy. Looking at number 10, let K be a positive constant. Which one of these is logistic? So when you have a logistic growth scenario, you are proportional to both the current population and the total population minus the current population. That's the number that are left. And there you have it. That is the only one of those that will actually model logistic growth. So that is D. And that's it for the growth problems. All right. Thank you. I hope you're well. And hey, that's the last topic in the BC course. So congratulations. We've gotten there. At this point, we do a quick assessment and some review, and we get ready to bring on the BC exam. All right. So thank you.